In today's video, we're going to cover the oxidation and reduction of alkenes. The first one of these reactions is ozonolysis, which we've already covered in lab, but I wanted to do a brief recap. And so there are two different ways we can do ozonolysis. They both start with ozone, O3, at minus 78 degrees. And then we can either do a reductive workup or an oxidative workup. There are a couple of different conditions for reductive workup. They include zinc and HCl or acetic acid or dimethyl sulfide, which Me2S. Those are the big reductive workups that we will see. And they result in cleaving this alkene and replacing each end with an oxygen. And so I have 1, 2, 3 carbons there, 1, 2, 3 carbons there, and I have my cyclohexane. And for a reductive workup, that's the end. If it's an oxidative workup, that's typically hydrogen peroxide. That has similar products in that we cleave the alkene, we put a carbonyl where the alkene was. The difference is this carbon has an hydrogen attached, and if there's a hydrogen attached to the carbonyl carbon, then we're going to replace that with an OH to generate the carboxylic acid. If there's no hydrogen, as in this cyclohexane, that gives the same product as the reductive workup because there's no hydrogen to oxidize. As a reminder from lab, I don't expect you to know the mechanisms of these reactions, but I do expect you to be able to predict the products of both the reductive and oxidative workups. The next reaction I want to talk about is KMNO4 and alkenes. And this can actually do a couple of different things. KMNO4, or potassium permanganate, if it's hot and concentrated, will give you the same products as if you did ozonolysis followed by oxidative workup. And so in this case, it would give you the carboxylic acid here, or the acetic acid, plus acetone, where we just cleaved this bond, and this half of the molecule went to form acetic acid, and this half of the molecule went on to form acetone. If, however, you use cold dilute KMNO4, you get slightly different products. So remember that KMNO4 is going to break up into a K plus and a permanganate ion, which looks a little bit like this. There's, of course, resonance, but I'm going to use that resonance structure. And I don't expect you to know the mechanism of this, but I'm going to show how this works for the first step. And so this pair of electrons is going to attack that oxygen, which is going to give some of its electrons to manganese, which is going to move these electrons here. And that is going to give you this intermediate that is a 5-membered ring that involves a manganese and 2 oxygens. And so that's the product after KMNO4. And then when you treat this with cold base, you cleave that manganese oxygen bond to form your final product, which is this diol, or I have added 2 OHs across that double bond. And so the reason I showed you this mechanism is so you know why this is the syn addition of a diol. And I also wanted to point out that osmium tetroxide, so osmium with 4 oxygens, or this molecule, can be used to do the exact same syn dihydroxylation of an alkene. If we look at one more example, if we add KMNO4 and cold and dilute to this alkene, we're going to get, again, syn dihydroxylation. And so we're just going to add OH to the same side of that alkene in both positions. So that is your final product for that. If, on the other hand, you use hot KMNO4 followed by some weak acid, we're going to cleave this double bond right there. To form the carboxylic acid, plus, in this case, CO2. And that comes from first this, but it's got 2 H's, and so we're going to replace each of those with an alcohol or an OH group. And this molecule is carbonic acid, which spontaneously decomposes into CO2 plus water. The next reaction with alkenes we want to look at is the last oxidation of alkenes that we're going to talk about. And this is forming an epoxide from alkenes. And so peroxy acids, or this functional group here, it looks like a carboxylic acid, but there's an extra oxygen in here, are very good at this reaction. And one of the most common peroxy acids we have is, are used for this reaction, is this one. And this is MCPBA, or metachloroperoxybenzoic acid. And it forms an epoxide out of this alkene. If we look at some arrow pushing, this is not one that I am super concerned that you know the mechanism for, but this is a syn addition here, and so I thought I would show it. I'm going to draw it in a little bit different conformation right above. And so what happens here is that alkene is going to give some electrons up to oxygen, which breaks that carbon or oxygen-oxygen bond, which pushes some electrons back to hydrogen, and that pair of electrons comes down, generating this epoxide plus the carboxylic acid. Of course, the epoxide is the only product that we're interested in. This is what we call a byproduct, and we're not as concerned about it. But it generates an epoxide. The epoxide formation is a concerted, that's a C. And so it's syn addition. Epoxides are useful in synthesis because it gives us another way to form a diol. And so if we look at this cyclohexene and we were to add MCPBA to this, remember that is a peroxy acid, and so it's going to generate an epoxide where that alkene was. And it's syn addition, and so both of those carbons, or that oxygen, is coming up from both of those carbons to generate an epoxide. And then if we take that and add a little acid and water, we can open this ring. And so the first thing that happens is this oxygen gives away some electrons to that H, which kicks them back up to the sulfate ion. To give you our third instance of a three-membered ring with a heteroatom with a positive charge in this hydronium ion. And then water is going to come in and bust that thing open from the backside to generate this intermediate here, which then a second water can come in and pluck off that hydrogen to give the final product, the dihydroxylation of that alkene. But rather than being syn, this is the anti-addition. And so thinking about notes on this mechanism, we have that three-membered ring with a heteroatom and a positive charge. And this gives us anti-addition of a diol. If we look at a couple of examples of the dihydroxylation of an alkene, in this first one we have MCPBA, which forms an epoxide, followed by an acid-catalyzed ring opening. This is going to give us net anti-addition of two alcohols across this alkene. And so I'm going to draw my alkene, or my skeletal structure, without the double bond in the same conformation. Notice that this methyl group is trans to the phenyl group. And then since this is anti-addition, I'm going to draw one alcohol on a wedge and the other alcohol on a dash. And so that is the anti-addition of an alcohol across that alkene, and this is going to generate this diol plus it's an enantiomer. Or if I draw it out, it would look like this, with this alcohol on a dash and this alcohol on a wedge. On the other hand, I have osmium tetroxide, which can do syn dihydroxylation of an alcohol. That reaction is going to look like this. I'm going to draw it in the same conformation, but I'm going to make sure now that my alcohols both go on heavy wedges, or they both go on dashed wedges, like so. And so these two things are enantiomers, and these two things are diastereomers. So anti-addition of an alcohol generates a different diastereomer than the syn addition of diols. The final reaction I want to talk about is the reduction of an alkene. And so the first thing is worth mentioning is that organic chemists think about oxidation and reduction a little bit differently. And so because this thing has a pi bond or a carbon-carbon double bond, we would say that this molecule is slightly oxidized. And we can use palladium on carbon plus hydrogen gas to reduce this alkene. And all that happens is we get rid of that double bond and we add 2 hydrogens in a syn fashion. So those 2 hydrogen atoms get added at the same time, and so this is syn addition of hydrogen atoms. I don't really care. In fact, we're not going to talk about the mechanism other than this is a syn addition. And I should note that a couple of other catalysts, including platinum and nickel, can do this reaction as well. If we look at another example of an alkene that does this, let's look at this alkene with an aromatic ring. I'm going to use palladium on carbon again and hydrogen gas. This reaction does not touch the phenyl ring. This thing stays intact and only reduces the alkene and puts 2 hydrogens on there in a syn addition again. Doesn't really matter if you draw in those hydrogens, but I want it to be explicit that they're there and that they added in a syn fashion. I think that's going to wrap up today's video. We will pick back up with some more examples in class next time.